Okay, deep breath.
Some announcements before we get started, because it's an important week in here. How is the current assignment going? I guess I can start with that before I dive into the rest of the announcements, since that is due tomorrow.
I like tomorrow. I've decimated it and I've tested, and I've been testing out the code a fair amount.
Good.
I'm not gonna turn in the main that I had default made with IntelliJ obvious, but yeah, I've just been testing it out to see if it works, and it turns out it does.
I haven't seen too many people in office hours about this, so I was expecting to see quite a few more people than I have seen.
Really? Well,
I don't know what that means, but either people aren't far enough to be stuck. I've just incredibly underestimated your abilities, and this is just incredibly easy for everyone.
well, the last homework was quite a challenge, and so that's why so many people were dealing with it. But with the coding thing, we're a lot more in our element, from what I see, based on your idea. And this is coming from some personal experience too.
Good. I'll have the couple hours after class for anyone who can make use of it. I, again, expect to have seen more people than I have. Hopefully that doesn't mean that everyone's procrastinating it to the last minute, because that will not end well.
I have no idea what you can talk about.
Well, fortunately, it's been anything but just kind of busy.
So there's that going on. We have an exam on Friday that we're going to start studying for tomorrow. This is just about that 24-hour point. So if anyone would like specific examples of particular material that we've gone over that you feel is the weakest material that we've covered for you personally, that you'd like to see some additional work done on, this is a great chance to either let me know that now in person or send me an email. Other than that, I will just field questions about any questions on the study guide, material on the study guide, suggestions for how to prepare, what to study, how to use the study guide, what to put on your note sheet, the kinds of questions that might show up on the exam. Those kinds of questions are all fair game for our review that will start tomorrow, and then we'll figure out at the end of class tomorrow whether we want to continue that on Thursday or whether we would like to go back to some other content and just get the exam over with on Friday. There will be another assignment coming your way. I don't know yet whether this is a 1 week or 2 week thing. I'll have to figure that out, but it is the next algorithm we're going to be going over after rod cutting. So over the next couple of lecture days, I will have you prepared, hopefully, to dive in and get your first experience writing an algorithm that uses dynamic programming. So that will be very fun. This algorithm is near and dear to my heart, so it'll be fun to talk about, and hopefully fun for you to implement. It was very fun for me to implement back in the day. Changed my perception of the entirety of computer science. Questions about anything before we dive back in? Away we go. Last time we talked about rod cutting as an intro idea behind dynamic programming. So hopefully we were able to see the repeated subproblems, how addressing the problem in a dynamic programming fashion allows us to fail to repeat that work, to store them in a lookup table and then look them up to save us a significant amount of time. We found that there were an exponential number of subproblems, but if we stored the subproblems as we went along, this immediately fell into linear time. We could figure this out in, I guess it's quadratic time if we're counting the number of potential, but it is quadratic, it is polynomial and not exponential, and that is a significant speed up. It goes from something that is infeasible for even moderately sized inputs to something that we can do for inputs of hundreds or even thousands, even tens of thousands. So what we did, we made sure we maintained a table of the costs of each of the subproblems. As we started thinking about solving those subproblems, we would look at the table before we go into that. Just look it up first. Once we solve a subproblem, it's the first time we're solving it, so we should add its solution to the table. Once it's in the table, when we see it in the future, we can just look it up. I looked at both the top-down and bottom-up solutions for this. There was a great question about why we would care to do both of these, or it looks like bottom-up is just way shorter and simpler. This is the iterative method. You can tell that there is no recursion in bottom-up. It's just a nested loop. And top-down is recursive in that we've split the two loops into two different functions. One of the outer loops is going to be the outer loop in this memoized cut rod, and then inside of that, we call the auxiliary, and that's going to be the other loop. There will be times when it makes more sense to work top down or bottom up. In this case, it probably makes more sense to work bottom up, but you may not know right away and have to think about whether it makes more sense to implement it one way or the other. So this is where we stopped. This is the last thing we went over, and then I wanted to look at the runtime analysis. So asymptotic runtimes of the implementations on the prior slide. I actually just spoiled this while talking about it, in that it is quadratic. If we look at why this is quadratic, let's actually go take a look at that. It's fairly straightforward. In the bottom up, we have a nested loop. The outermost loop runs n times, and the innermost loop runs a number of times proportional to the size of the outermost loop. So the innermost loop will run once the first time the outer loop runs. It'll run twice the second time the outer loop runs. So we end up with 1 plus 2 plus 3 plus 4 plus 5. That same progression that we've seen about 5 times now in this class by itself. And we know that's n squared plus n over 2, which is quadratic. If we go over to the recursive implementation, now it's a little bit more challenging because it's not a nested loop. We can't just multiply like we could have before, but we can get a sense just at a high level analysis that the loop in memoized cut rod is going to run n plus 1 times. And then we need to return for each of those the auxiliary cut rod, and that is also going to run, there is a loop inside of that from 1 to n. So this is also going to run with proportion to n times n times. We could go through the substitution method for this and try to break down into how complicated are those subproblems. That's a little bit more work than I'm planning for in the middle of lecture, but that would be a good study problem if you're looking for working on this ahead of the exam. Come back, look at these slides, look at this problem, and see if you can come up with a good substitution method and solve it.
Well, only problem, we can't access them right now.
Not yet.
Yeah.
Hopefully by the end of the day.
Just speaking my mind.
So we already saw the flaw here, I think. Did we talk about this? We may have talked about this. But the flaw in the code itself still is the same flaw that we saw before, that it only returns the sale price. It does not tell us how to break the steel rod down into its associated lengths that get you that price. So we need to make sure that we store the path that we take through the optimal solution as we calculate it. This becomes one of the more difficult things to implement in dynamic programming once you understand the breakdown of the problem. The question is, as you are solving the problem, how do we store the subproblems, the actual path that we took through those subproblems as we calculate them? So let's start by looking at bottom up. What do we need to change? And I'll go back to the code on the prior slide. What do we need to change about that code in order to store the appropriate cuts as we figure that out? So let's go back. Let's zoom in on bottom up and take a look at how we would modify this code in order to know the path that we took. Take a couple minutes, feel free to talk to people around you.
You think? I'm not entirely sure either, but basically need to figure out like, I don't know. I was thinking maybe some sort of. Hey, no. Well, somehow we need to store the pathway, which would be. We have to show how the rod is. Sure about the answer itself.
Any thoughts? So we know that we're making an array. For the elements of that array, we're figuring out for cuts of size 1 up to the size of the query, we're going to store the optimal cost in this array. So when we finish the first pass through the outermost loop, we know the optimal breakdown of a size 1 query. After that, we know the optimal breakdown of a size 2 rod, and then a size 3 rod, and then a size 4 rod. Do we actually know the breakdown? We know the cost. We're storing the optimal cost in this array, but we don't have the breakdown. Where have we figured out where that optimal breakdown is? It's in the innermost loop.
Yeah, most likely.
So as we calculate Q as the maximum, we care about where this Q came from, which side of this maximum we are using. When we update Q to be a new value, we need to store something else. The fact that we updated Q with a new piece of information rather than an old piece of information, then we need to update some kind of reference to how that cost was acquired. So we would probably need either some additional data structure to store the breakdowns, or an augmented data structure where we don't just have an array, maybe we have some kind of two-dimensional array that tells us yes or no, or how many, when we're looking at breaking down a rod of size 5, what is the optimal breakdown of a rod of size 5? How many slices of size 1, 2, 3, 4, and 5 do we have for that? Yeah.
Would it have to be something recursive?
What's nice is it's already embedded in the format that we have here. When we make one of these changes, we know exactly where it would have come from in the associated structure. A 2D array is probably, it's an interesting idea, it would work. But we need something right here. When we make this change, we basically need to surround this with some kind of if statement to figure out where the maximum is coming from. So let's go back and take a look at what that solution looks like. So here is that if statement. Inside the innermost loop, we need to see where that max comes from. If it comes from new information, so the current value of Q is less than the new breakdown that we are looking at when we look at a new potential. So we're looking at when J equals, let's say 3, we're looking at the optimal way to break down a steel rod of size 3. Then we would be looking for 1 up to 3. we're looking at what is the cost of each of 1 and 2 and 3, as well as the possible breakdowns for that. If we find that our current best breakdown for that value is less than looking at the potential breakdown of making a cut there or not there, so we're looking for P of I, R of J minus I, then we will be able to find whether this is something new. If it is, then we'll store that, but in this array S, this will tell us that pointer. We're storing a back pointer to when we want to look up a breakdown of size 3, this is where that breakdown goes. And when we print the solution, now we look through the S array, and the S array will store the path of that breakdown. When we break down a 5, what is the next thing we break it down into? We break that down into a 3. And that's all stored there in a way that we can recreate the solution. Let's take a look at how this would work as an example. So here is when we call print rod with 10, it just prints 10 because that is the best possible breakdown. But n equals 7 prints the cuts 1 and 6. It tells us where the cuts were made at each potential location. So at each location, the question is, are we making a cut there, yes or no? And this now breaks down into the recursive subproblem. Does that make sense? I can try to draw this out if this probably needs some kind of
Please do.
augmentation. Yeah. So where I have a little bit of space. If we're trying to call with this n equals 7. So this tells us that we have a steel rod of size 7, and there are potential places to cut this. It's going to end up looking exactly like an array. There's position 1, 2, 3, 4, 5, and 6 as the places that we could make a cut for size 7. And we're going to break this down recursively to say that if this is the best place to make a cut along this, we can cut at any number of locations, but if we make a cut here, then we're looking at the size 1 versus size 6. And that would have to be optimal based on the breakdown of recursively breaking apart this steel rod of size 6 into whether we could make cuts at position 1, 2, 3, 4, or 5. If this is optimal, then the value, the best way to break this down, plus the best way to break this down must be the best way to break that down in order to have a cut at that location. When we do recursively look at the size 6, we can now break this down and say, is it best to make this cut, this cut, this cut, this cut, etc. You don't necessarily just make one cut, but we're going to store when we have a subproblem of that size, where are we making the cuts? So we can see from within here what this is the cost that you get, the total value, and this breaks down into where the first cut is. So this tells you that when we start with a subproblem of size 7, this 1 tells us the first cut should be at position 1, breaking this down into a 1 and a 6. We can now recursively look back at S of I for 6, and it tells us the first cut is at 6, which tells us to not make a cut. Because the only legal places to make cuts are 1 through 5. 6 says don't make a cut. So just from this lookup, this tells us the optimal breakdown of a problem of size 7 is just making a single cut to a 1-inch steel rod and a 6-inch steel rod. How this table was constructed is just by adding this if statement. So we're going to figure out, are we making a change to the optimal breakdown as we've seen it? If we do, then we're going to write that into the S array as saying that is the new best place to make that cut into the associated subproblems of those sizes. We will never make more than one cut at a particular level because the recursion is going to handle the additional cuts. Let's see if we can read this for a different problem. Let's say we have the problem of size 9. Well, size 9 is boring. Size 8 is also boring. These are all boring. I want it to be inherent in the table here. 9 works. None of these really are that exciting, it looks like. But how do we read this? We start with an array of size 9. Where do we make the first cut?
The third spot.
At 3. So this is going to give us a size 3 and a size 6. If we recurse to size 3, what do we see?
Cut 3 of them.
Yeah, don't cut at all. Because the options are 1 and 2 for the middle points. So this says don't cut. If we look at 6, that also says don't cut. So this is the optimal breakdown for a rod of size 9. But we got that information from filling out this table. And note that we solved every other subproblem along the way. So if in the future we stored this table and then in the future had a reference for how do we optimally break down a rod of size 8, that's inherent in the table we already calculated for a prior problem. We don't have to restart and recalculate this whole thing. We could just now analyze the breakdown as 8 should break down into 2 and 6. 2 stays by itself, 6 stays by itself. That's inherent in the table as well. I feel like for understanding, it's probably best to break down exactly how this is working. So maybe we could run through this for a very small example for filling out a very small table. Let's see if we can do something like j equals 3, right? N equals 3. We do n equals 3, then j is going to the outermost loop. It's going to look at and fill out the optimal costs for each of 1, 2, and 3. You can see that in this outermost loop, the last thing we do is fill the value of the R array. So the last thing we're doing is coming up with the optimal cost that we can get, the optimal sell price we can get for a steel rod of that size. So we're going to go through some work, and at the end of that work, what we're going to have access to is that optimal breakdown. But we're not going to know where it came from unless we store it as we make the changes in this innermost loop. So going through the innermost loop, we're going to now go from I is 1 to j. So this first time when j equals 1, so let's start with j is 1, I is 1. This is the only time we're going through this innermost loop. Q starts out as small as it can possibly be so that we guarantee the first time we're doing something. So let's look at if Q is less than P of I, which is the price index, the one table we don't have access to. I would like to also have that here, but we're looking up the price of a single cut rod, size 1. So we get 1 plus the current R of j minus I. R of j minus I, 1 minus 1 is 0. That's that initial value that we store there. So 1 plus 0 is 1. Is 1 greater than negative infinity? Yes. So we come into the if statement and we set Q, the current optimal value, to that value, 1 plus 0, as its default. Then we're going to set S sub j, S sub 1, to be this 1. So that's how we derive that value. Loop back around, innermost loop is done. We set the R to be this value, the optimal value that we calculated. And for a rod of size 1, there are no further breakdowns to make, so we don't have to worry about it. Okay, now we loop back around the outer loop. We're going to set j to 2. Q gets set back to negative infinity. I is 1, we'll go up to 2. We're going to ask, is Q, currently negative infinity, less than P of I, the price of a rod of size 2? Do we remember what a price of a rod of size 2 was? I think it was 3. I'm going to run with that assumption. And I think it must be 2, because we end up with this 5. Yeah, that makes sense, considering this value is 5. So we're going to say P of I, the lookup for that, which is 5, plus R of j minus I, J is 1, I is 1, so we're looking at the 0 again. 5 plus 0 is 5. So we're going to set Q to be 5. Then we're going to set S sub J to be I. So this S sub I is going to be S sub J, which is 2, is currently I, which tells us the optimal breakdown for this rod of this size. It should have been I in the first place. I'm doing the next pass through the second one. This should be 1 plus J minus I is still, yeah, this starts out being 1, saying that the best breakdown here is looking at 1, and Q in this case is the price of 1 plus that, which gives us 1. So this starts out being 1 and 1. And this makes sense for if we break down a size 2 rod into 1 and 1, then the breakdown is going to be 2 different recursive procedure calls where the cost is 1. When we loop around and set I to 2, now we're looking at whether this 1, which we've now set, is less than a lookup of P of I, which is now 5, plus 0, which gives us 5. 5 is greater than 1. So we're going to say that this now came from a rod breakdown of size 2, and the total cost we can get here is 5. So we start iteratively building up the values of this table by looking at prior values that we've calculated in the table. We're doing lookups when we break down the problem to figure out the overall cost of that. Does that help that make a little bit more sense, hopefully? Kind of reading the code, going through and seeing how this is filling in these tables. This is the trace back for where this goes when we break this down. What is the first cut that we make? And then this is the overall cost of the optimal breakdowns. When we make a cut of size, or in a rod of size 5, we know that the values of the optimal breakdowns of 4, 3, 2, and 1 are all stored in this table, so we can look them up. Since we already calculated the cost, we don't have to do any further work. So this, again, is that dynamic programming at work. Checking in with people, how do we feel about this code and this table? Show of thumbs, maybe?
I think I at least understand.
Somewhere between middle and up. Okay.
Okay.
I think I'm okay with that. Nothing says I'm horribly lost. Sometimes it just means that we need to go back and take a look at this in more detail, trace it on your own.
Okay, yeah, I get it.
So print cut rod at the bottom, all it's doing is going through this now augmented structure. When I said we were going to use an additional structure, it turns out that a second array is the best thing that we can do. We can now read how the answer should be broken down because of this. So given that we have a rod of size 9 that we want to cut up, this tells us the cuts to make and the total cost. So now we know exactly how to break it down to get that cost, which is an important part of dynamic programming. All right, we're going to go into sequence alignment because this is the fun problem. I'm diverging a bit from the book because the book goes into matrix multiplication from here. And one way that I can just describe the problem is that when you're multiplying matrices, you end up with potentially vastly different costs associated with those matrix multiplies. So instead of just multiplying one matrix by another matrix, instead imagine that you have a chain of 10 or 20 matrices that you need to multiply. And at any point, we could multiply any 2 matrices that are adjacent to each other in that list, and we end up with a matrix of the appropriate dimensions to be able to multiply with the matrix that comes before it or after it. But the order in which you do that can change the total number of multiplies in that process by orders. There may be a problem where you can do 100 multiplies and solve the matrix chain. There may be that same sequence, if you do it in a different order, may have 100,000 multiplies in order to solve the problem. So we want to find the optimal breakdown of the order in which to multiply the matrices in order to minimize the number of multiplies to get the solution matrix. That is an excellent way to think about dynamic programming and an excellent example, but given the math background of people in the class, I wanted to use something that was a little bit less mathematical in practice. If you have a bit more math background and would like to check that out, go ahead and read that section of the book. It's extremely useful and relevant here. But I'm going to introduce an algorithm out of bioinformatics, computational biology, for sequence alignment. If you have interest in this, you may be interested in applying computer science to biology. There is an entire field that does this called bioinformatics. The question at hand with sequence alignment is the relation of two organisms to each other. If you look at something like these particular DNA sequences, and they look relatively similar, one in a snake, one in a cow, but exactly how similar are they? We would like to be able to place some kind of numerical relation to these two sequences.
What? Most of it is the same. Plenty of it isn't.
Yeah. So if we just look at these as strings and look at comparing these strings to each other, then we can find that there are sections of this that are relatively similar. There are sections of this that are relatively different. How can we do that? So we'll call a string, we'll just call it a finite sequence of characters. We can look at the length of that string, number of characters in that string, length of S. A string is defined over some alphabet, the legal characters that can appear in that string. So the DNA alphabet is 4 characters. The English alphabet is 26 letters that can be uppercase or lowercase or digits or special characters. This is why we have our ASCII table. But different alphabets have different subsets of characters, different numbers of characters, and that can tell us a lot. So the alphabet for DNA is just A, T, C, and G. The alphabet for RNA is A, U, C, and G. The alphabet for amino acids, quite a few more. We can denote the empty string as just the string that contains no characters. Let's look more at strings. Let's say we have 2 strings, S and T, and those 2 strings utilize the same alphabet. We can concatenate those 2 together, ST, all of the characters in S followed by all the characters in T. We could say that S is a substring of T. If we could break this down into potentially empty strings, U and V, such that now T is U, S, and V concatenated together. So S is somewhere inside of T. That S is found somewhere. And there could be characters before that, there could be characters after that, but we know that that string is found somewhere inherent in the other string. We can call a subsequence, S is a subsequence of T, if the characters appear in order in the string, but not necessarily in the same consecutive. So here is the word vacation. Cat is a substring of vacation because the letters CAT appear in the middle of it. In this case, according to our definition, U is VA, the characters that appear before cat. V is ion, the characters that appear after cat, but CAT all appear consecutively in the middle of the word somewhere. So cat is a substring of vacation. Can is a subsequence because they appear in order, C followed by A followed by N, with optional characters in the middle. We know what a prefix and suffix are if they're a substring that appear at the beginning or end of the word. So basically, if U is empty and S is a substring of T, then S is a prefix of T. If V is empty, then we have a suffix. Any questions on any of this preliminary work? Hopefully most of it's review. Okay, how do we compare strings? We have two strings, we'll call them A and B. We can break them down into their individual characters. So A is made up of a concatenation of characters. A sub 1 is the character at the first position in string A. A sub M is the character at position M in string A, and we'll do the same thing for B. Note that we use two different variables for the lengths of A and B because they may not be the same. So A has M characters, B has N characters. So A sub I and B sub I are letters from the alphabet. If we're using DNA, then each of these characters have to be characters that would appear in the alphabet. And the goal of sequence alignment is to compute a similarity metric. How similar are these two strings by some definition of similarity? So we need to define similar in order to do this. And there are many ways that we can do this depending on what the goal of the algorithm that we're writing is. So one of them could be the concept of edit distance. The fewest number of operations that we would need in order to transform one string into the next string. So we could replace a character, which is a mutation. You could delete a character, or you could insert a character. So what is the edit distance between riddle and triple?
Well, they both have the I and the LE in them, just. You see some differences. Oh, actually, yeah, they have RI and LE in them, but they got the two D's parts.
Three.
Gonna be a 3
Yeah,
at a distance of 3. That is correct. A few ways you could do it, but one such way: delete one of the D's, mutate the other D into a P, and then insert the T at the beginning.
oh, okay. Oh, okay, now I get it.
So edit distance, you can again mutate, delete, and insert. And we can do things like assign weights to these, because depending on what we're doing, it could be that there are different costs associated with mutations, deletions, or insertions. Some of them may be more likely or more computationally complex within that domain. So as an example, in DNA, if we're looking at the evolution of a DNA strand over time, then mutations replacing characters are more likely or more frequent than deletions and insertions. So we can assign different weights to these based on how much work it takes for a natural phenomenon to occur. And this allows us to place weights on the edit distance, that some of these operations are cheaper to perform, some of these operations are more expensive to perform. And then when we calculate the similarity becomes weighted now based on how easy or how difficult the elements of this edit distance are. So what we're going to be doing with one sequence is we're going to try to manipulate it into the other sequence, but we're going to have weights associated with each of these that allow us to come up with a customized similarity metric based on how likely these biological phenomena are. Questions? Does that make sense? All right. Let's now break this down into the inputs and outputs of the algorithm we're going to talk about. So the parameters, we're going to have a gap, the concept of a gap. A gap is placing it's basically an insertion into one string. So we're trying to map do something like A T into A C T. It's obvious that we want to match the A to the A, we want to match the T to the T, but we want to match this C to a gap. We're inserting space in this A blank T to insert this C in the middle. So the similarity would have two matches and one insertion. So this is the concept of a gap in a DNA sequence. So it's the cost of inserting that dash character or an insertion or deletion as we translate one string into the other. We need the concept of a cost, the cost of aligning a character with another character. There can be two ways to align. We can either find a match or we can find a mismatch, and we need scores for each of those. So if we align a character with another character and that character is a match, there is a match bonus. If we align a character with a different character in the other string, there's going to be a penalty to the score based on a mismatch. Goal of the whole thing, we want to compute the edit distance, finding, according to these weights, the lowest cost alignment or the highest scoring alignment between two strings. The overall cost of an alignment, we can break this down recursively into the cost of the pairs of characters as we have either matched them, mismatched them, or created insertions or deletions in one string in order to change one string into the other. So that sum of a character by character comparison is what will get us the score of the alignment. And we want to find the alignment that has maximum score. Given that we have two strings, how many possible alignments are there between those two strings? Yeah. And possible alignments? Good guess. Yeah.
Would be n times n.
Even higher than that.
Yeah.
It is exponential. For each character in the first, we can either match it with the first character that's match it or mismatch it, or we could add a gap. And that works for each of the characters, both in the to string and the from string. Gap in the first string, match what's currently there, gap in the second string. And we do that for each character along the line. That gets us an exponential number of possible alignments. But there is one optimal alignment. If we're going to brute force this, it's going to take us a very long time to look at every possible character aligned with every possible other character with the potential for gaps thrown in there. So this tells us that we need some kind of dynamic programming if this is going to scale, especially if we hope to ever align any DNA sequences that are the lengths of DNA sequences. Since there are quite a few characters to that, and if we are using an exponential time algorithm, we're never going to find that optimal alignment before we perish. A computer won't find it before we perish. So each string is a set of nodes. We're going to visualize this as a 2D array, but you can also visualize it as a graph. We're going to go over graphs in a lot more detail in a bit. But we're going to align starting at the very beginning rather than trying to look at the entire two strings. We're going to start with basic alignments. But you can imagine that now what we're trying to do is exactly this. Match, mismatch, or gap in order to align one sequence with another. So you delete a character in one, you're inserting a gap into the other. You're inserting a gap into one. then you're deleting a character in the other. Now, note that the strings may not be the same size, so you may be doing insertions of gaps in order to make them, like the AT and ACT example from before. We needed a gap to turn the AC into the same length as ACT in the middle. And the best we could do was align the A at the beginning and the T at the end. So if we wanted to do and figure out the cost of this possible alignment, we would see that we have a match, a gap. How do I do that? Gap, match, 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 mismatch. It's a big M. Match, 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 gap. Match, 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 match. And if that's the best we can do, the total score we would have here is the number of little m's times the match bonus, the number of big M's times the mismatch penalty, the number of G's times the gap penalty. And that would be the score of this alignment. And again, there are an exponential number of possible alignments, so we want to find the alignment with the highest possible score, and we don't want it to take exponential time.
Yeah, actually, how long do you want it to take? Or do we need?
I want it to take constant time. That's impossible. But we can end up with a quadratic algorithm for this.
Alright, well, this is why I'm asking these things, thank you.
Yeah.
It could be constant, we just ignore the input.
Yeah. So yeah, of course, edges can't cross. We can't match things across. Like insertions or deletions don't allow us to match something. It's the same thing like trying to solve a word search by circling individual letters. As cool as that would be, that's not the format that it's supposed to be in. So if we're aligning two sequences, biologically, what happens are we end up with a conversion of one nucleotide into another. We end up with an insertion or deletion, but we don't ever have teleportations or swaps within the strand of DNA, so we don't allow for it in our matching. So you can also think of it as being an editor. You're working left to right, and how the editor would either match or mismatch. So you would match, replace, insert into, or delete from as you move left to right. So that's one way to think about it as well. You can also think of it as an alignment, the way that I have been drawing it out. And this ends up being particularly useful because there is an entire database of DNA sequences out there. And the invention of this algorithm allowed us to be able to parse the DNA that we've stored in this database efficiently. I have mentioned that there are an exponential number of alignments, but this is the way to visualize it. This is a log scale here on the left. So even though this looks linear, the rate at which this is going up is exponential.
Well,
So when your y-axis is exponential and the graph looks linear and the x is linear, then you end up with an exponential curve. This is one way to more easily visualize a very quickly increasing exponential curve. You take the y-axis, you stretch it out into a log scale, and it stretches that exponential curve down into something that is linear. And we see that we end up with a term here that is 2 to the k times m choose k times n choose k, and you sum that from 0 to the minimum of m and n. And that is the end for the number of possible alignments in this. So there are a ton of possible alignments.
wowzers.
That is absolutely huge. And you can see that for a string of length 100, there are 10 to the 70 possible alignments, when there are only 10 to the low 80s number of atoms in the observable universe. So this is a reasonable portion of the way there.
Wow.
So to be able to solve this problem in polynomial time and force a string of length 100 to be solved in under a second, compared to how many possible alignments, it'll find the best of 10 to the 70 possible alignments in under a second. And so we'll come back to this possibly next week, possibly later this week, and actually see how it is done.
All right. Alright.
Office hour starting now. From whomever I can help, however I can help you.
Okay. I have got a lot of work today. Let's start. Charlie turned in the last.
Yeah.
That night,
About that. See what I can do. I'll take a.
I was gonna-
Something to go across the path.
Yeah, I was gonna try to tackle most of it today anyway, but it would just be nice to have a little bit more.
The concern I have is that I don't want people focusing both on the open and the exam at the same time.
Yeah.
So. I'll think about it, especially because I haven't covered quite enough this to assign it yet, and if we don't do anything for the rest of the week, then I can't reasonably make this due next week. So I'll think about it, and I'll either make some kind of announcement or reach out to me individually and I'll see what I can do.
Yeah, if I'm struggling, I'll like, we'll send you a message tonight or tomorrow.
And Gabriel, yes, I will upload this. If you could send me an email to remind me of that, I'll make sure that I get to that as soon as I can.